We have every reason to be proud of what we've learned about the universe so far, both over the course of these lectures and over the course of the past 100 years as working physicists and cosmologists. We know that the total energy density of the universe is about the critical density, what you need to make the universe spatially flat. We know that of that density, it's about 5% ordinary matter, 25% dark matter, and 70% dark energy. We have a great theory for what the ordinary matter does. We have the standard model of particle physics, which tells us what the particles are and how they interact, consistent with all the experiments we've done here on Earth so far. We don't know what the dark matter is, but we have more than enough different candidates. It's not a surprise to us or a deep mystery how you could get dark matter to be 25% of the universe. We have lots of different ideas for what it could be, and furthermore, we have very good ideas about how to test those theories, ways that we can create the dark matter in particles individually, and also to detect it coming from outer space here to our detectors on Earth. So now is the lecture in which we face up to the fact that the dark energy is not so simple. The dark energy is something about which we do not have very good ideas about what it might be. We're going to spend 3 lectures looking at different possibilities for why the universe is accelerating and spatially flat, why we seem to believe that there is dark energy, at the end of which you will realize that none of the theories are especially promising. None of them are like the case of supersymmetry in the case of dark matter, where you have a theory that does other things, naturally provides you with a candidate, and whether it's right or not is at least a very plausible scenario. So let's think about exactly why we think that there is dark energy. We have a set of evidence for it. That evidence is very different than the evidence we have for dark matter. The dark matter evidence comes from the local dynamics and behavior of stuff in the universe attracting other stuff. We have galaxies, we have clusters of galaxies, gravitational lensing, the growth of structure in the universe. All of these say there's more stuff here in those bound systems than there is outside. If we naturally attribute that to cold, non-interacting massive particles, we seem to fit the data. Dark energy, on the other hand, is found globally. We look at the acceleration of the universe due to the kind of stuff that is inside it. We look at the spatial geometry of the universe, which is a way of measuring everything all at once. We find that if we imagine that 70% of the energy density of the universe is smoothly spread throughout space, taking the same amounts inside clusters and galaxies and outside, and also persistent as a function of time, not redshifting or diluting away as the universe expands, we can fit all these data all at once. So we call this mysterious new substance dark energy. So what could it be? The 2 things we know about dark energy are that it's smoothly distributed through space and nearly constant in time. Therefore, certainly the simplest thing it could possibly be is something which is absolutely 100% the same from place to place in space and the same from moment to moment in time. The data are not yet telling us that that is precisely the case. The data are, of course, consistent with some slop in that conclusion. There could be small variations from place to place. So that's going to be the subject of the next lecture. This lecture is going to be about the possibility that it really is truly constant. And the physical underpinnings for those 2 possibilities are very, very different, even though their observational signatures are pretty much similar. So we should say, before we go there, that even though we're going to contemplate in this lecture the possibility that empty space has an absolutely constant energy, known as the vacuum energy is a candidate for what the dark energy could be. These are not synonyms with each other. The dark energy is the label given to whatever it is that is out there in the universe that is smoothly distributed and persistent, 70%. The vacuum energy is a specific idea for what it might be, the energy of empty space itself. It's still possible that what we call the vacuum energy is 0, and what we call the dark energy that is making the universe accelerate is something else entirely. But for this lecture, we're going to concentrate on the possibility of vacuum energy. So what do we mean by vacuum energy? We mean the energy of empty space itself, but what does that mean? That means that you take a little region of space, a little cubic centimeter, and you remove from it everything you can possibly remove from it. So it's completely empty. You remove all the ordinary matter, all the dark matter, all the radiation, all the neutrinos, so there's really literally nothing there. And you ask, how much energy is contained inside this cubic centimeter? In the context of either general relativity, our best theory of gravity, or quantum field theory, our best theory of microscopic physics, there's no reason why the answer to that question should be 0. There is some number, some constant of nature, which tells us how much energy there is in every region of empty space-time. So this picture that you're seeing here is actually an artist's impression, my impression, of what dark energy, vacuum energy, is like. You can think of it as a false color image of empty space itself. Of course, empty space is really completely dark and invisible, completely see-through and transparent, so this is just an attempt to make you contemplate the idea that even in this little bit of empty space, there's still energy there. The energy is not contained in some substance that is located there and could be moved around. It's inherent in the fabric of space and time itself. That is the idea of vacuum energy, the bare minimum amount of energy you can fit anywhere. There's nothing you could do to that cubic centimeter, no physical process, which would lower the energy below that. So what do we mean by the energy of empty space? We're saying over and over again the same words, the energy that you have in an empty cubic centimeter of space, but you're still sitting there thinking, what does that really mean? To a physicist, when you say, what does that mean, you're asking, what does it do? How would we know that it is there? Is there some operational, observable consequence of saying these words? And now we get a little bit of a subtlety, actually, because in almost all areas of physics, the actual value of the energy doesn't matter. What matters is how much energy changes when one process happens, the energy that goes up or goes down, or the energy that gets exchanged between two different ways in which it can manifest itself. For example, you might be familiar from high school or college physics with experiments like an inclined plane, a ball or a box rolling down some inclined plane, and people will talk about the energy that is contained in this ball rolling down the plane. It will have potential energy, depending on how high it is, and kinetic energy, depending on how it's moving. And if everything is very smooth, there's zero change in the total energy. You're just converting potential energy into kinetic energy. But here's the thing. If you ask, what is the total amount of energy of that ball rolling down the plane, it doesn't matter what the answer is. If you did exactly the same experiment from the plane being right here, the ball rolling down, or raising the plane up so it's up here, the potential energy of the ball would change, but the way in which the energy goes from being potential energy to kinetic energy wouldn't change. And of course, the motion of the ball down the plane would be exactly the same, whether it was up here or whether it was down here. As long as the tilt of the plane is the same, the local physics is exactly identical, the total amount of energy that the ball has is completely irrelevant. So you might say, even if there was empty space energy, vacuum energy at every point in space-time, how would we know? The answer is that gravity is the one thing in nature that really does care about the absolute amount of energy. Remember, Einstein tells us that gravity responds to everything. Gravity is universal. And so what's going to turn out to be the case is that the amount of energy that is contained in empty space doesn't affect anything about, for example, the standard model of particle physics. The only thing it affects is gravity. It acts to curve space-time. It creates a gravitational field. That's how you can detect it. That's how, in fact, we're claiming that we did detect something like it by looking at the curvature of space and, of course, the acceleration of the universe. So what is the effect of this vacuum energy? We've already said that it makes the universe accelerate. If there's some energy density in empty space, that energy density doesn't go away as the universe expands. It's a constant. It's a constant of nature from place to place and from time to time. So as the universe is expanding, this vacuum energy is giving a perpetual impulse to the expansion of space, and we perceive that as the acceleration of the universe. There are other effects. If you had infinitely good measuring apparatuses, you would be able to detect the existence of the vacuum energy using all sorts of gravitational experiments. The classic experiment that lets us test general relativity in the first place is the motion of the perihelion of Mercury. The planet Mercury moves around the Sun in an ellipse, and according to Isaac Newton, that ellipse should be fixed in orientation once and for all. If you put aside perturbations from the other planets and imagine a perfect solar system that just has the Sun and Mercury, that ellipse is exactly the same for all time. Einstein comes along in general relativity and says that that ellipse should change slightly. That was actually already known to be the case. Before Einstein came up with his theory, astronomers had already determined that Mercury was slowly shifting in its orbit. That is a way in which we were able to tell that general relativity was a better theory than Newtonian gravity. It turns out that if you had a vacuum energy, you would also add a small new effect to the motion of the planet Mercury. However, that effect, when I say small, is really, really small. There's no possible way we will ever be able to test the possibility of vacuum energy by looking at Mercury. It's just swamped by things like me sneezing here on Earth. There's a million bigger effects than the vacuum energy when you're thinking about how Mercury moves around the sun. The reason why we can detect the vacuum energy in cosmology is that because the effects accumulate. When you're looking at the motion of a galaxy or the supernova in some galaxy, there are many, many cubic centimeters between us and that galaxy. And every one of those cubic centimeters is expanding just a little bit faster because of the presence of vacuum energy. It's that accumulated effect over cosmological distances enables us to actually detect the fact that the vacuum energy is there. The first way the physicists started thinking about this concept of vacuum energy was actually going back to Einstein himself. Einstein, soon after inventing general relativity, started thinking about cosmology. He knew that he had a very different way of thinking about space and time than Newton did. Isaac Newton had a picture in which space and time were both fixed and absolute. Einstein has a picture in which space and time have a geometry. They're dynamical and they can change. So he started thinking about the entire universe. As a simplifying assumption, we're now talking 1916, 1917, 1918, long before we knew the universe was expanding. Einstein took as a simplifying assumption that the universe was pretty much the same everywhere. He found that within that possibility, that the universe is pretty much the same everywhere, he was not able, with his equation governing the curvature of space and time, to find a solution in which the universe was static, in which it was smooth everywhere and more or less staying the same as time went on. Now we know today the reason why, because the universe is in fact expanding. It is not static. And that makes perfect sense. If you have galaxies spread throughout the universe, they're going to pull on each other. In the context of Newtonian gravity, if you try to ask the question, what could happen if you filled space full of galaxies, the same number everywhere, would they pull on each other or not? It's very hard to get an answer. On the one hand, you might think that yes, they're pulling on each other, therefore they should come together. But there's an equally plausible looking analysis that says, here I am, this galaxy, every other galaxy is pulling on me, but they're equally distributed, the net force is zero and I don't move. Nothing moves. Within general relativity, there's a different answer that says, you can think about nothing moving, but space itself can get bigger or smaller. So in general relativity, if you have nothing but matter in the universe, the answer is unambiguous. Space better be either expanding or contracting. Now, there's a little bit of a false story that goes around about Einstein thinking about exactly these issues. It says, Einstein was blinded by his philosophical presuppositions. He wanted to believe, this false story goes, that the universe is static for some religious or philosophical reasons. And therefore, when he found that his equations didn't describe a static universe, he was upset and tried to change them. The truth is that he did believe the universe was static, but it wasn't because of a philosophical predisposition. It's because he asked his astronomer friends. At that time, in the 19-teens, in between 1915 and 1929, as far as anyone knew, the universe was static. That was what the observations were telling us. It wasn't until Hubble in 1929 discovered the fact that there's a relationship between the velocity of distant galaxies and their distance, did we realize that space is in fact expanding and dynamical. So what Einstein was trying to do was to fit the data. He thought the universe was static. He showed that his own equations did not allow for a static solution if you just imagined a universe full of galaxies, or even full of matter of any sort. So what did he do? In 1917, he changed his equation for general relativity. He added a new term which he called the cosmological constant. Now these days, we consider changing Einstein's equations to be an interesting step, but a dramatic one. We have very good success with those equations. But you have to remember that Einstein himself was coming up with new equations all the time. In fact, the final version of his equation was not anywhere near the first version of it. He was changing it to fit things both philosophical and experimental all along. So finally in 1917 he said, well, I can add a term to the left-hand side of my equations. So here are, of course, Einstein's equations. On the left-hand side you see the term that tells you how curved space and time are. On the right-hand side you have the term representing stuff in the universe, energy and momentum and so forth. Einstein put a new term on the left-hand side for which he could then find a solution that the universe could be filled with galaxies and yet not expanding or contracting. The solution that he called the cosmological constant, we now know that you can move to the right-hand side and it's exactly the same as vacuum energy. In fact, there's some people who like to argue whether or not this term deserves to be on the left-hand side with the spatial and space-time curvature bits, or deserves to be on the right-hand side with the energy bits. Of course, the truth is it absolutely makes no difference whether a term in an equation is on the left side or the right side. It functions in exactly the same way and has the same interpretation. Einstein would have called it the cosmological constant. We will call it the vacuum energy, but it is the same thing. So vacuum energy acts to make the universe accelerate. It basically pushes things apart as the universe expands. Ordinary matter pulls things together. So basically all Einstein did was find a solution where those two effects exactly balance. Now it's true, he could find a solution where the universe was not expanding or contracting, but of course his solution was unstable. If you perturb it a little bit, if things just started moving together a tiny bit, the pulling together force would win and it would collapse. If things started expanding a little bit, the pushing apart force would win and things would start accelerating. So Einstein found a solution that fit the data, but it wasn't a physically plausible solution. It wasn't something that was robust to small changes in what happened. Then, of course, in 1929, Hubble comes along and says, well, the universe is not static, it's expanding, just as Einstein could have predicted in 1917. According to George Gamow, who later was one of the primary thinkers about the Big Bang model, Einstein later claimed that his biggest blunder as a scientist was to introduce the cosmological constant into his equations. If he had not done that, he would have made a prediction. He would have been able to say, despite what the current observations say, circa 1917, I predict that the universe should either be expanding or contracting. But he blinked and he wasn't able to do that. He then said, away with the cosmological constant, I'm sorry I ever invented it. But once you do that, you can't undo it. Pandora's box is not so easily closed. These days, we realize that what Einstein called the cosmological constant is what we call the vacuum energy, and we can start asking questions like, if there can be energy density in empty space, how much should there be? Can we make some sort of reasonable estimate for how much energy there should be in every cubic centimeter of space, the minimum possible value? Well, it's a very fuzzy story that goes back and forth. There is no precise answer to this question. What should be the vacuum energy according to our current theories? The true answer is it can be anything at all. It is a constant of nature. It's like saying, what is the mass of the electron? There is no ahead-of-time answer to what it should be. You have to go out there and measure it. On the other hand, there are reasonable answers and unreasonable answers. We can do a pretty good job of estimating order of magnitude how big the vacuum energy should be. We have both what we would call a classical contribution to the vacuum energy, the thing that it should be if you ignored all of quantum mechanics, and then, as we'll explain, quantum mechanics adds new contributions on top of that. Together we get an estimate, we can compare it with what we see. The answer is, it's nowhere close. The estimated value of the vacuum energy is much, much larger than what we observe. So let's think deeply about why that is true. First, we need to talk a little bit about quantum mechanics. Quantum mechanics is the correct theory of the world, as far as we know, at least the correct framework in which to be thinking about the world. It replaces Isaac Newton's classical mechanics. In both classical mechanics and quantum mechanics, you have physical systems, and those physical systems do things. They evolve, they obey equations of motion. The real difference between classical mechanics and quantum mechanics is that in classical mechanics, you can observe everything there is to know about the system. So if I have a system that is a ball rolling down a plane, or a pendulum swinging back and forth, or a set of springs, I can measure where all of the components of that system are. Then I can use the laws of physics to predict where they will be in the future and where they were in the past, in principle, to arbitrary accuracy. In quantum mechanics, meanwhile, there's a rule that says you cannot measure all of the properties that a system has. In fact, you are dramatically unable to measure. Think about a coin, which you can flip, and will be heads or tails. While it's still spinning in the air, if you asked, well, is that coin heads or tails? Classically, it's somewhere in between. It's rotating in between being heads or tails. Quantum mechanics is like a coin which you flip and it's rotating in the air, but nevertheless, every time you look at it, it's either exactly heads or exactly tails. It's not that we don't know which one it is. It's that when you're not looking at it, it is some superposition. It is neither heads nor tails. It is described by some angle. But when you look at it, you never see that angle. You always see it to be exactly heads or exactly tails. For a more realistic example, think about a particle like an electron. An electron, classically we would say, has a position. It's located there, and it has a velocity. It's moving in some direction. According to quantum mechanics, it's not that we don't know what the position is. It's that there is no such thing as the position of the electron. What there is a function of space called the wave function. And the wave function tells us, if we look at the electron, where are we most likely to see it? What is the probability of finding it in different places? But the true answer to where the electron is not a question that has an answer. There is no such thing. When you look at the electron, you always see it in a position, but when you're not looking, it doesn't have a position. It has a probability of having different positions. That is the origin of uncertainty in quantum mechanics. What you can observe is not what there really is, but what there really is, this wave function, tells you the probability of getting different answers to your observations. So let's apply this to a very specific system, which is not exactly the real world, but it's a good analogy for the real world, and that's a simple pendulum. Just a weight that can rock back and forth. It can be stationary, just sitting there, or it can be going back and forth with some amplitude and some frequency. This is a good classical thing. This is exactly the kind of thing that Galileo used to look at when he was falling asleep in the cathedral in Pisa, and he would time the pendulum with his pulse, because he didn't have a very good clock back then. But these days, what we've learned to do is to take classical systems and quantize them, to put them in a quantum mechanical framework and see what happens. In the classical pendulum going back and forth, it has energy. It has a potential energy depending on how high it's gone up, and it has a kinetic energy depending on how fast it's moving. Furthermore, those two things, the kinetic energy and the potential energy, can take on absolutely any value. In quantum mechanics, on the other hand, two things happen. One is that the energy cannot take on any value. It takes on certain discrete values. That's why it's called quantum mechanics. There are specific energy levels that you can see. You can't see anything in between them. The other thing is, if you ask what is the lowest energy level, you get a different answer in quantum mechanics than you would have in classical mechanics. In other words, all you're saying is, here's a pendulum, put it in the zero energy state. Put it in the state of minimum energy. Classically, it's kind of obvious what to do. You stop the pendulum from moving. You make it sit there, so it's located at the bottom of its trajectory, its potential energy is minimized, and there's no kinetic energy. Quantum mechanics says that that would be the same as precisely specifying the location of the pendulum, and you can't do that. Therefore, the minimum energy configuration still has some uncertainty in where it is, and therefore still has some uncertain energy. So this idea of a pendulum is actually quite analogous to the quantum fields that we have in the real world. A pendulum has, classically, energy. Quantum mechanically, it has a slightly higher minimum energy than classically. What we have in the real world are fields oscillating through space and time, but it turns out to be quite a good approximation to think of the field at every point in space as a little pendulum going back and forth. It has a kinetic energy, it has a potential energy, and quantum mechanically it has a little bit more. But I want you to notice two things about this analogy. First, if you ask what is the energy of the pendulum, just like the inclined plane, there's no right answer. The potential energy of that pendulum would change if we moved the whole apparatus up by a foot. But none of the physics would change. None of the laws of motion of the pendulum would be altered in any way. The quantum fields in space-time have exactly the same property. There's a minimum amount of energy that you can ascribe to them that is true classically, even in empty space, and it's a completely arbitrary number. But then what quantum mechanics says is that on top of that completely arbitrary number, there's also some quantum mechanical jiggle. Quantum fields have the same property. In addition to the completely arbitrary answer to the question, what is the minimum energy, quantum mechanics adds an extra contribution to that minimum energy because of the fact that the fields are jiggling back and forth. This is just Heisenberg's uncertainty principle, the fact that you can't localize a quantum mechanical system with absolute precision. Because of that, there will always be quantum jitters. In the case of a field, like the electron field or the electromagnetic field or the gluon field, these jitters carry energy and they contribute to the energy density of empty space. They contribute to the vacuum energy, in other words. Now there's a rule in quantum field theory. When you look at a field, what do you see? Just like for a single electron, you have a wave function, but when you look at it, you see a particle. For a quantum field, you see a collection of particles. A quantum field is basically a bookkeeping device that tells you how many particles there are all over the place. So you might think that if I have a quantum field, its vacuum state, which to physicists means its lowest energy state, the state I can put the quantum field in that has the least energy I can possibly have, would have 0 particles. If there are particles, then you have some energy there. The vacuum state of the field, the lowest energy state, should have no particles anywhere. It should just describe empty space. And that is correct in the sense that there are no particles in empty space that you can see. Nevertheless, Heisenberg and his uncertainty principle are telling you there are particles that you can't see. We call these virtual particles. The fact that you can't pin down the quantum field to some precise configuration is telling us that you can't avoid virtual particles popping in and out of existence. These virtual particles are not a new kind of particle like we already have electrons and quarks, now we also have virtual particles. They are the good old particles that we know and love, photons, electrons and positrons and so forth, fluctuating in the vacuum, fluctuating in empty space itself. These virtual particles certainly exist. This is not some crazy hypothetical thing. It was a crazy hypothetical thing 70 or 80 years ago, but since then we've detected the effects of these virtual particles. They interact with ordinary particles passing through empty space. And the effects of these interactions change the atomic energy levels in ordinary atoms of ordinary stuff. They give rise to corrections to formulas in particle physics, and these corrections have been tested to exquisite accuracy. In other words, we have a picture in quantum field theory of empty space in which empty space is not boring. Empty space is alive, popping, with virtual particles and antiparticles that appear and then disappear. We can't see them directly. We can't pull a virtual particle out of the vacuum and make it real. But we can tell that they're there because they have effects indirectly on the behavior of other particles. For example, they have effects on gravitons. These virtual particles have a gravitational field. They carry energy. And that energy that they have is precisely the vacuum energy, a contribution, if you like, to the amount of energy density in empty space. What we said then is that just like for a pendulum, if you ask what is the minimum energy of empty space, there are 2 contributions. First, there's a completely arbitrary classical number. There's some number there in the laws of physics that says if quantum mechanics weren't true, the vacuum energy would be such and such a number. We have no idea what that number is. We also have a quantum mechanical uncertainty, a 0-point energy of the vacuum fluctuations of every field in the universe added on top of that. Now, what is this energy? How much is the shift in energy from quantum mechanics? There, we can at least estimate it. So even if we didn't know the classical energy, you might imagine that the quantum mechanical shift was of the same basic size as the original vacuum energy. So it turns out that if you do a naive estimate of how much energy quantum fluctuations add to the vacuum, you get infinity. So that's not right. But in quantum mechanics, infinities happen all the time and we know how to fix them. We put on some cutoff, we stop including contributions from very, very, very short length scales where space-time itself might dissolve into some sort of quantum foam. Then once we have that cutoff, we get a finite answer for what the quantum mechanical contribution to the vacuum energy is. And in terms of numbers, it turns out to be 10 to the 112 ergs per cubic centimeter. That is a lot of ergs, and erg is a measurement of energy. If you ask, given the data, given the observations from cosmology, how many ergs per cubic centimeter are there, the answer is 10 to the -8th ergs per cubic centimeter. In other words, our best guess, our best estimate on the basis of modern physics of how much energy there should be in the vacuum is 10 to the 120 times bigger than the amount that we actually see. 1 trillion, 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 trillion times bigger than what we actually see. That's a theory that does not match the data. This is called the cosmological constant problem, and is probably the largest unsolved problem in theoretical physics. We had known for a long time that there was a cosmological constant problem, long before we actually detected the vacuum energy. It was obvious that the vacuum energy was not nearly as big as our naive estimates said it should be. So we had that problem. But before we detected the acceleration of the universe, the best idea was that there was some secret symmetry of nature, some secret mechanism that took this huge vacuum energy you should have and exactly canceled it, made it equal to zero. Even though we didn't know what that symmetry was, it didn't seem like such a stretch that someday we would detect it. But now that we've found some vacuum energy, now that we've found some dark energy that we can attribute to the energy density of empty space, the problem has become much harder. We don't want to multiply the real number by zero, we want to multiply it by 10 to the minus 120. It's as if you see someone on the street who is flipping a coin, and they flip a coin and they say, do you think it's going to be heads or tails? And you say heads. And they flip it and it's tails. And they flip it again and it's tails. And they flip it 299 times in a row and it's tails every time. You don't know why. You don't know what the mechanism is. But if they then say, I'm going to flip it again, what do you think it will be? You're going to say tails. And they flip it and it's heads. Something made something go away. Something made the vacuum energy disappear 2 to the 299 times, but then there's a leftover there that 300th time. This tiny amount of vacuum energy, by all rights, shouldn't be there or should be bigger. We're stuck with a situation where it's there. So it might be right. It might be that once we finally understand everything, we get a better formula for predicting what the vacuum energy would be, and we get the right answer. Right now, we're simply at a loss. If the cosmological dark energy is the energy of empty space, it's an idea that fits the data, but about which we have no understanding. Therefore, we're going to try other things. We still don't know why the vacuum energy is small, but maybe it is zero. Maybe the actual dark energy we're seeing is something dynamical. That's what we'll be exploring in the next lecture.